Yeah, I think so. Oh, yeah, there's sound.
Hello? Yeah, I think we can start. Hello, everyone. Welcome to our faculty candidate talk today. Today, we're really glad to have Professor Zhaohui Geng from Department of Manufacturing and Industrial Engineering at the University of Texas, Rio Grande Valley to visit us. His presentation topic is From Statistical Learning to AI, Modeling, Inference, and Control for Advanced Manufacturing. And Professor Geng, he leads the Cyber Manufacturing and Smart and Connected System Division at the University Center for Advanced Manufacturing Innovation and Cyber Systems. And regarding the research interest, he focuses on intersection of data science, artificial intelligence, and optimization with application in reverse engineering, additive manufacturing, metrology, and production systems. A little background of Professor Geng. He received his PhD in industrial engineering and a master in statistics from University of Pittsburgh. So let's welcome him to give us this talk.
Thank you, Kaibo, for the introduction. I think the microphone is working. So for this talk, we'll talk about statistical learning. We'll most focus on statistical learning, but based on my previous work, and then we move on to the artificial intelligence of my current work and how they can apply it for the advanced manufacturing settings, right? A little bit background. Everyone knows about this. Industrial revolutions is currently we are experiencing Industrial 4.0, which is a very fancy word. Regarding Industrial 4.0, there's the key point or key objective is to eliminate the lines between the biological, digital, and physical worlds, right? And also we are experiencing some preview of the Industrial 5.0, which we will talk about later in terms of our artificial intelligence part. Now let's focusing on Industrial 4.0 and see how what are the major topics under this area for advanced manufacturing, right? So in general manufacturing setting, the two major worlds that we are talking about, like we want to blur the lines, is the digital world and the physical world, right? So for my talk, we're focusing on the digital world. We talk about the design, computer-aided design for the physical part. And the physical part is that we directly fabricated from this design, right? So from the digital world to physical world, we have a very well-marketed technology, state-of-the-art technology that is additive manufacturing that we can directly utilizing a design and transform into the physical world to get the product, right? The other way around, we have, because in the digital world, we're talking about design. So we have the 3D scanning and reverse engineering, which is utilized to extract the geometric features from the physical part and translate it into the digital world, right? And the more general umbrella would be computer vision, right? So because we are focusing on the other way around about the reverse engineering, we'll talk about additive manufacturing later. Let's take a look at what is the manufacturing processes regarding the reverse engineering technology, right? So a typical reverse engineering processes look like this. So we start from a physical part. We utilize reverse engineering to reconstruct the CAD model, and then we utilize additive manufacturing to reproduce this part, right? Here I give you an example about the dental applications. We utilize the scanner to survey the intraoral environment so that we can have the whole bridge or some dental implants for the patients. Now we have a big question over here is regarding whether this reproduced part can be implemented to the patients, right? So that is, we need to consider whether there's any geometric variation along this process. So we have, different variation components along this process. We have the variation due to the reverse engineering process. We have the variation due to the additive manufacturing process. Because this intraoral environment is so very complex, it's generally considered as a free-form surfaces with, even some intricate features. So how to model this becomes a real challenge for these type of applications, right? Now let's move on to a more general manufacturing setting. So we have this part. We want to survey this and to get the model, and then we reproduce this part so that it can be assembled in the real applications, right? So we still have all these errors embedded into this system. At the same time, we have new challenges. That is regarding the uniqueness of the reverse engineering, that if to get this part, there's an original unknown production system, and also there's an unknown original design governing the whole process, right? So there's some tolerance specification, geometric dimensioning specification, which is heavily unknown. So which comes to a question like whether this reproduced part can be assembled into the real application and whether it's usable, all right? So to tackle these issues, we need to find a way to model these variations and find a way to estimate the original design, right? So in order to do that, we need to know what type of data we're dealing with, right? So the data we're dealing with is called point clouds. The reason we choose point cloud is that it provides detailed geometric description for complex features. Nowadays we have all kinds of fancy design tools such as topology optimization. We have shape optimization can help us to generate very intricate features and generate freeform surfaces, right? On the other hand, additive manufacturing is superior in producing these features, which give us a challenge how to measure these deviations, right? So point cloud can provide us with some very detailed description of these features that generally cannot be described by these parametric models. But also, even for simple features fabricated by the additive manufacturing, classic or conventional measurements or conventional metrology cannot be utilized. The reason, let me give you an example, right? So here we have a very simple box-shaped design. The conventional way to measure this side surface is to utilize this endpoint. Its n is at least 3, so everyone knows that 3 point is governing this flat surface, right? So generally, we utilize this endpoint to measure those. But additive manufacturing, we are producing this part layer by layer fashion. So if we are still utilizing the 3 point or even endpoint measurements about this side surface, this one only gives us some information about these different layers rather than the whole feature, right? On the other one, more extreme case here is that if we change the build orientation to an arbitrary orientation, all the surfaces are not directly fabricated. If we still utilize this 3 point measurements, this only gives us partial geometric information of those layers and also partial information of the features, so which is not very useful to control or monitoring the additive manufacturing processes, right? So therefore, we adopt the point cloud to give us a very detailed description. Now, if we determine we utilize point cloud to do this analysis, so what are the point clouds, right? Point clouds is a very common data type for 3D vision, for reverse engineering, for 3D scanning. It's actually quite simple. It's just a set of points on the part surface, and each point is described by the x, y, and z coordinate. But at the same time, there's some challenges when analyzing those, right? So the first challenge here is a large volume. So let's take a look at this simple, relatively moderated complex geometric features. We have over 1 million points to describe the details within this feature, so which has a very high dimensionality of this point cloud data. The other one is actually a complex data structure. It's one type of shape data in 3-dimensional space, so every point is spatially correlated, right? And also it's watertight, so it's a little bit hard when compared to the general computer vision tasks. And also, the most important thing is the lack of correspondence. Meaning if you use the same part, you do two type of measurements. The point clouds, the points you surveyed are located at different positions, and also there's a lot of variations according to that. And also the number of points is very different. So lack of correspondence, meaning we cannot utilize the currently available analytical tools to solve those. Right? So our challenge is, first of all, how can we model this uncertainty in the point cloud? And then if we can model this uncertainty, how can we make decisions based on this model? Right? So therefore, our major contribution is lying around to developing this this volumetric data analysis framework that can translate the unstructured data into a structured format. The idea we utilize is actually we adopted from the statistical shape analysis community. It's called landmarks. The landmark is determined to be the point of correspondence among different population or within the population, right? So here the population can be among different parts or among different scans, right? So we start from the data collection. So the point cloud data can be surveyed through the reverse engineering or can be directly generated from the STL file. And then the next step is that we want to do a landmark generation. So we actively generate some point cloud replacement that is much well structured, and then we do the analysis on top of it. And then we utilize the registration to remove some unnecessary factors, such as rotational and translational factors, which are irrelevant to manufacturing quality control. And also we have the statistical estimation and inference based on the after the registration. The registration actually doing two tasks. The first one is removing the rotational and the translational factor. At the same time, is performing a space transformation. It's transformed from the configuration space into a new space called size and shape space. And then, based on this statistical estimation, we can do some applications, which we will talk later. Right? So now let's take a look at these three major steps, how we can develop this framework based on that. Right? So the first one is landmark generation. Again, we want to transform the unstructured data into a structured type. So this is the first algorithm we developed. It's called characteristic plane projection, which meaning we have a full point cloud. We first do is feature segmentation. So we segment the features of whole point cloud into a subset of features. And then for each feature, we generate a unique plane to this feature, and then on top of this plane, we can generate grid so that we can project these grid points back to this feature. So all these points is of correspondence, right? So we have two types. First one is a supporting plane, which meaning all the feature points is above this plane, while the distance is minimized. So it's unique to this feature. The other one is more robust. That is, we utilize principal component analysis to find out the first two principal components of this feature because the global variation of the feature is more robust. So therefore, we can utilize these two components to generate the plane, right? But this has some issues. Right now this one is good in a way that we can directly generate a lot of point cloud replacement. But at the same time, the issue comes from the first step, that is feature segmentation step. Right now, according to the development of feature segmentation for point cloud, is still not that robust. There's a lot of noise for a relatively simple features, so there's some issues with this. So to build up on this idea of landmark generation, we develop a new algorithm called Bright Slicer. This one is a funny story behind this. We have a breading machine at home. One day I'm slicing this bread. I found out this one can be utilized for point cloud, landmark generation. So the whole idea is that we treat this whole point cloud as a whole, and then we cook a bread or cook a envelope that's unique to this point cloud, and then we slice it along all three directions, right? So after slicing it, we have a frame that is generated from the envelope, and then we also have a profile of that layer, right? And then we generate the grid on top of this profile, and then we can have the point of correspondence along this, utilizing this algorithm, right? So this is a landmark generation. This one is still, we are still working on this. This one is doable for some features, but if we have some more complex features, there's something need to tune, and also we want to fine tune it for high precision manufacturing settings, right? So the next step is the registration step, meaning we want to remove the unnecessary factors located in the point cloud. That is rotational and translational factors. The parse is a parse. No matter whether it's located, it's still with the same dimensions, right? So therefore, we need to have this registration step. The most popular one by the statistical shape analysis community is called partial progressive analysis. It's basically a least square problem, with respect to the rotational matrix and also the translational vectors. This is good. It's very computational efficient. It's converged after a few steps. The most important thing that we adopt in this registration step is because it transforms the landmark from the configuration space into a new space called size and shape space. We'll talk about the nice statistical property in this space later, but this one is very widely adopted by our framework, right? But still, we are not fully satisfied with this algorithm. The major challenge here is that this algorithm is good, but everyone knows about least square is generally very computationally efficient, but it's not very realistic, especially considering the high precision manufacturing. Because the deviation in the geometric dimensioning and tolerancing standards are very well defined to be the maximum deviation about this feature, right? So therefore, we also developed another algorithm called minimax registration to align with this standards principles, that is Taylor's principle, that every deviation should be defined to be the minimum envelope between the 2 point clouds. So therefore, the envelope meaning is maximum deviation. So therefore, we model this to be a minimax problem of this maximum for each point respect to these point clouds, right? So our minimization step is taking on the rotation matrix and also the translational factors, and also maximum is taking a look at all the points, all the pairs of point clouds. Right? Generally, a minimax problem is very hard to solve. So fortunately, we can reformulate this problem into a second-order cone programming by some small tricks. Here I present some preliminary results. Here we have a one-on-one comparison to mimic the quality inspection scenario in manufacturing. So we can see that the red line is the performance of our algorithm, and the green line here is not quite obvious, but the green line is the iterative closed point, another very popular algorithm, and the blue line is the partial progressive analysis. So you can see that for any pair, our proposed minimax registration algorithm outperforms the rest two, right? So this one is good. We are still deriving this, especially in terms of the statistical property in the new space, we call it the minimax size and shape space. We're still deriving the distribution. Our best guess is that in the space, if we have a truncated normal, we're still working on that. But let's come back to the partial progressive analysis. Why this one? We adopt this one for the future work, right? It's governed by this theorem. This theorem is very interesting because it was developed several years ago. It's not that popular by the statistical shape analysis community, but we find out this one can directly suitable for manufacturing setting. The idea is that if we do the partial progressive analysis, if the landmark variations is much smaller when compared to the global variations, then we have these two nice property after registration. Right? So the first one, instead of going into the theorem, I kind of help you to summarize these 2 points. The first one is that after registration, the coordinate of each landmarks has a multivariate normality, or at least approximately multivariate normality. So which is we can directly utilizing this normality to do error modeling. We can have a very good performance in terms of principal component analysis. And also, the other nice property is that we have a coordinate-wise independence, which meaning rather than dealing with high-dimensional matrix, we can vectorize it into a high-dimensional vector and to do further analysis, which can save a lot of effort, right? And also we can also do this coordinate-wise parametric bootstrapping, which is very useful for uncertainty quantification for tolerance applications, right? So with this framework, now let's move on to how can we applying this framework to real applications, right? So this is a nice framework, but how can we apply it to solve real problems in reverse engineering and additive manufacturing, right? So the first one, let's talk about reverse engineering first. The first problem we're talking about is the process planning for reverse engineering. So in other words, is that we want to, our objective regarding reverse engineering is how to reconstruct the original design, and how can we quantify the uncertainties in the estimation for this original design with a relatively small batch of point clouds, right? In real practice, generally we have a limited number of scans, and we have a limited number of parts. So that's why we need to have a way to dealing with this small batch of point clouds. Right? To do that, we need to first understand what are the variables and how we can control them in this modeling, right? So we identify that in the reverse engineering hardware, there's some accuracy issue. There's no way to model them. Luckily, we have the VDA framework, so we can actually model the accuracy of this reverse engineering hardware. And also regarding the accuracy of the original manufacturing or additive manufacturing processes, it's also if the part is there, then you can do nothing about this part, so we can find a way to model these variations, right? So the variations is there, so how to tackle this issue? This idea is actually quite simple. Everyone takes a statistical course, at least one statistical course, right? Everyone knows that if you take one single observation, the variation is generally large. If you take the sample average or the sample mean, it generally performs much better than each individual observations. Right? So we are mimicking this simple idea to see if we have multiple scans and we have multiple parts, and as if we can take a simple average, whether it has give us a better estimator to the original design. Right? So the idea is quite simple. And also, if that one is a success, then our next question would be how many scans we need and how many parts we need so that we can reach some of the practical considerations about these reverse engineering projects. Right? And the other one is that how we can model these variations. If there's an unavoidable variation, how can we model these variations and incorporate that into the process planning for remanufacturing systems? Right? So let's tackle the first issue, like how we can model this accuracy, these variations inside the scan or inside the part, and utilizing the limited number of resources. Right? So the way we do that, we model the whole problem in a Bayesian way. That, again, we have a likelihood model or coordinate model is that based on the theorem, we can model each coordinate as a multivariate normal distribution. It's governed by two parameters as the mean vector and also the covariance matrix. The way we do that is that we have because we have limited number of scans or limited number of parts, right? So we cannot, if we directly take the average, it's fine, but it cannot guarantee that what the performance looks like. Right? So therefore, we want to incorporate some domain knowledge into this modeling so that the model can converge faster than before. Right? So here including the standard deviation of the scanner, which comes from manual, and also some guess of the standard deviation of the original production system, so that we can, analyzing the feature, how it's machined, so we can have some prior knowledge into that, and then we have this weakly informative prior. The reason we call it the weakly informative prior is for the mean value is if you take a look at these priors, there's nothing related to the mean vector, so we have a non-informative prior for the mean value. For the covariance matrix, we have embedded some information about the prior knowledge, but still it's very weak. Right? We let the data speak by themselves. Right? So this is a setup for this Bayesian modeling, and then we derive, because we're considering the mean value should be the original design. Right? So it comes from the same population, so the mean should be the original design of this part. So we derive the posterior marginal distribution for these mean vectors, and we identify two nice properties with this posterior. First one, if we take a look at the mean value is actually a simple mean. So according to our idea, if we take the average, it should be converged to the true design, right? The other one is more interesting, is about the covariance matrix. If you take a look at the denominator, oh, by the way, I didn't mention that M is the number of parts, N is the number of scans. So which meaning, if we take more parts and take more scans, the variance can be reduced along the way. So this kind of verify our idea. If we take multiple scans, may take multiple parts, the estimator should be outperform each individual observations, right? With this setup, now we can talk about the process planning. So we have a bio-objective optimization model. So we want to minimize the total number of parts, minimize the total number of scans to save some resources, and constraints-wise, we want to have the part model and scan model is within the accuracy requirements. Right? So we can write it mathematical like this. Here, to avoid any confusion, we have a small symbol here. The reason is that when you do the reverse engineering projects, we generally start from a few parts and few scans rather than finish the whole project. right? So we have a small trick to extrapolate our estimation in terms of the covariance matrix with these limited resources so that we can propagate to a large number, so that it will adapt our objective function. Right? So let's take a look at some of the results. First one, we have a simulation results. So here we are talking about two cases. One is for the biomedical applications. We have a unique part. We want to do multiple scans to have a better precision model, right? So here we can see that the trend is obvious. Like with the number of increasing part, the maximum deviation is actually decreased. And also the red line here is our target in terms of the precision. So we can see that with our process planning model, each of the stopping point is below this precision requirement, meaning the maximum deviation has already reached the requirement. For the several parts model, here we are mimicking the remanufacturing processes. So we have multiple parts, and each part with multiple scans. And then here we have a similar pattern, so with different accuracy requirements. We have a decreasing trend if we increase the number of parts, and also each of the part model will reach the precision requirements, right? And also one of the things is very interesting, is that this trend is not linear. So we have some elbow effect. So if we want to do further, like in real practice, we can directly identify where the elbow is changing. So we can utilize that one for real practice. Right? So let's take a look at some case studies. The first one, again, is mimicking the biological applications. So we have a unique part fabricated by the fused filament fabrication process. So we want to do a measurement of the true dimension of this additive manufactured parts. So we can see that the pattern here is the same. So we have this elbow effect with increasing number of scans. The average scan model is the same as the one that's measured by the coordinate measuring machine. And also, according to this table, we can actually calculate with different precision requirements, we have different number of scans. But one thing that you notice here, if we control the scan accuracy to be 0.005, we need 104 scans. In real practice, this one is impossible. 27 scans is also impossible in real practice. So we'll talk about later how can we do uncertainty modeling and incorporate that into the process planning. Right? Another case study is, again, mimicking it's the same as the remanufacturing process. We collect a few parts from the Manufacturing Systems Center at University of Pittsburgh. We have the original design, so what we do is we utilize CMM to measure each part and take the part model to see whether it's closer to the original design. Right? So here we can see that the pattern is the same. With an increasing number of parts, the part model is closer to the original design. Right? So, and also the table here is showing that we have, with different precision requirements, we have different number of parts. Again, here, if we control the precision to be 0.03 millimeters, 132 parts are needed, which is, again, impossible in real applications. Right? So rather than doing this process planning, another way to think about is that if we have limited resources, how can we model this uncertainty for each of the point clouds, and including that when we're doing the remanufacturing processes? In other words, originally we have a very wide tolerance specification for the feature. Now, with this consideration of the variance, so we can reduce that tolerance, so we have a tighter tolerance for remanufacturing processes. Right? So to do that, we start from the scanning products because that one is more doable. So what we do is that we build a automated variance modeling for the 3D scanning process. So to do this variance modeling, we need to know what are the factors influence the point cloud variance, right? So with some prior knowledge, with some experience, and also from the prior studies, we identified the three major fields that influence the variance. The first one is the scanner hardware. In terms of the laser types, the different structure light patterns, and also the environment, which is humidity. There's different factors influencing the performance of the scanning products. But we identify those are controllable factors because those factors you can optimize before you conducting the scanning products. The one thing that we definitely not control is the object. If you fix the objects, then the whole scanning product is useless, right? So we are talking about 3D scanning for any objects, especially the geometric design of the objects. when we talk about the color, material, and coating, we can apply the same material of coating or the same color to the different material or to the different parts, and then we can do the scanning to optimize the scanning experience, right? But in terms of geometric design, we definitely cannot control it, right? So therefore, our objective is to see how we can build a model between the geometric design to the variance of the point clouds, right? So to do that, we need to understand what is the mechanism behind this scanning laser scanners, right? So here we have this is a mechanism of the laser scanner. It's quite simple. So we project the laser strips onto the surface of the object, and then we collect the reflection utilizing a CCD camera. The variation is actually appearing in this area, how this laser interact with the material, right? So we identify 3 major factors in this area. The first one would be if this curvature of this area is very large, meaning this area is very small to be surveyed by the laser, then the variance should be higher, right? The other one is that if if this angle over here, this one is an inflection and reflection angle. If this angle is too small, this one is also very hard to be surveyed, so the variance should be higher. The other one is that regarding the height is actually here. If the height is very low, meaning it's closer to the scanning table, so there's some reflections from the scanning table to the part will interfere with the scanning laser, so the variance should be higher, right? So here we have empirical study over here. So we have a free-form objects. We do 30 scans of the same object, and here we have the variance value. So you can see that we have a large variance around that region. That region is because the normal direction of the point is perpendicular with the scanning laser strip, so it's really hard to be surveyed. And at the same time, it's closer to the scanning table, so there's a lot of interference from the laser strip reflected from the table. And also, this one is not quite obvious, but there's small light color around this region. That one is caused by the high curvature in that region, in the design. So therefore, our objective is to build a model of the variance with respect to these 3 factors. It's summarized as the angle of the normal direction of the landmark with the z-axis, which is scanning direction, the rate of local curvature change, representing the curvature of that feature, and also the height of the measurement, right? So here we have do a small tricks in statistical analysis that we utilize the logarithm to project the positive value to the whole real line. Right? So now we need to find a model to describe this unknown functional relationship between these features and the response that is variance. Right? This one is a very nonlinear, relationship and also quite complex. So our first thought is to utilize neural network. But the issue is that with the neural network model is that first of all we are facing millions of points, and also not mentioning the tedious hyperparameter tuning for this neural network model. So rather than doing that, we adopt the extreme learning machine, which is a variant of the feed-forward neural network, that rather than training all the parameters in the input layer and output layer, we randomly assign some random values for the weight on the input layer and only train on the output layer. To get a better control, we utilize a Bayesian way to do that on the weight in the output layer. But still, this one is because we totally randomly assign the weight in the input layer. Even with the Bayesian way, it's still really hard to control. So we are proposing some variants of this framework, of this model, so that we increase the extrapolation and interpolation performance. So we utilize 2 ways to enhance the performance. One is the ensemble version, is mimicking the random forest. So we train a set of models and taking the average of their prediction so that it has a more stable performance for extrapolation. And also we have the residual version that is stacking all the networks vertically, which is a residual training on the next network which is mimicking the generalized linear models, right? But still, there's these models outperform other models. We'll show you the result later, but there's still some issues, right? So in the reverse engineering projects, we need to choose a training history or training objects to fit this model, and then we can predict the test model. So if you have a set of different objects, how you select the appropriate one to be the training history, right? So therefore, we also utilize, these ideas from machine learning. So if your training set has a similar feature distribution as a test set, the performance should be comparable. right? So therefore, we utilize this modified KL divergence with extra penalty on the extrapolation and the interpolation region to find out which is the most appropriate objects can be utilized for the training history, right? So let's take a look at some experimental results, right? So we have 3 training objects, half ball and 2 free-form surfaces. If you only eyeballing this design, you can see that the free-form 2 is, geometrically approximate to the test object. But turns out if we utilize modified KL divergence, we find out even though this one is a little bit nothing like the test object, but in terms of feature distribution, it's very similar to the test objects. So our hypothesis, this one should have the best performance when compared to the half ball and the other free-form objects. And actually verified with our table here. So here, according to this table, of course, in the original paper, we do all kinds of comparisons with our model, with other, more very popular machine learning models such as feed-forward neural network, with Gaussian process models, with XGBoost, with other machine learning models. So our model have a very comparable, even not better, if not better, performance with other models, and also with very small amount of time for training and prediction, right? And also here I show that the ensemble version, the residual version of the Bayesian extreme learning machine outperforms the original single Bayesian extreme learning machine, also much better than the repeated measurements, right? And also I can verify that freeform 1 has the best performance in terms of prediction, outperforms freeform 2 and half ball, and freeform 2 has a better performance when compared to half ball because it has a relatively a value that's closer to 0 for this metric, right? So this is about the variance modeling. So you learn about this, so what it can be applied, right? So let me show you one intermediate application of this algorithm. It's related to the printing or scanning. So in printing and scanning, if we do not change the design, the one way that can influence the variance is to change the orientation of this object by which can cause a change of the normal direction, which is a parameter for our Bayesian extreme learning machine, right? So therefore, our solution to increase the precision would be if we have a rotational table or we have a pre-designed wedge to change the angle of the part, whether we can increase the performance of the scanning task or printing task, right? So here we applying a rotational matrix to mimicking this rotation table or printing table to change the normal direction and feed into the Bayesian extreme learning machine. So we can see that for this half ball objects, the traditional way is place on the table, print it or scan it. Now we compare it with our Bayesian, of our optimized version. So we can see that this orange, line, brick line, shows that this is optimized results. It has a much smaller maximum deviation when compared to the traditional way, right? So, and also because this our proposed model, this one is a black box. We can do a conventional way of optimization, but we think it's very time consuming. So we utilize a Bayesian optimization to do that with a softmax approximation in the objective function, because here we are optimize a min-max problem, right? Now it's a good time to shift our focus a little bit from reverse engineering. I think you learn a little bit about the reverse engineering. Let's shift to additive manufacturing a little bit, right? So for additive manufacturing, the whole process is very similar. Instead of having reverse engineering, let's rename it as a metrology to get the physical the point clouds of the printed parts, right? Now we can actually feedback, utilize this point cloud to feedback into the process or into the design so that we can have a better manufacturability through process analysis, or we can even change the design. Similar, the previous slides I show you only changing the direction, build or scanning direction will influence that. Not mentioning if we change the design, whether we can have a better performance, right? And also we talk about the sustainability and manufacturability by design, so we change those a little bit, and then it can prolong the use life of the part or have a better manufacturability of the part to have a better performance, or we can directly embed some security through the design, by changing the design features, right? So this one is more like a long-term goal, but let me introduce one fundamental problem in this, before we go diving into this, right? This one is a very fundamental problem for, that is hypothesis testing for additive manufacturing with freeform designs, right? So because of the VDA from framework, each point cloud, each scans can be modeled as a multivariate normal distribution, and then we are talking about the geometric accuracy of this under different process settings, right? So therefore, the whole problem, if we have different process settings, we want to compare their performance, whether there's any difference between their performance, the whole problem can be written as a hypothesis testing regarding the mean matrix, right? So a little bit recap. To do that, to do this hypothesis testing is, is fundamental problem, but at the same time, it's actually a quite complex problem because we're talking about hypothesis testing regarding high-dimensional matrix, which is generally a hard problem. Right? So let me give you a recap of the theorem we mentioned before, right? So the first one, we have two nice properties, basically. We have a coordinate weight independence, meaning we can do a vectorization of the matrix, and also we can do a multivariate normality. We have the nice multivariate normality, meaning we can have a very good performance regarding principal component analysis, and also we can introduce the Hotelian's t-test if we can project it into a lower dimensional space. Right? So the first equivalent form of the original hypothesis test is the vectorization. So we can directly vectorize the high-dimensional matrix to have a high-dimensional vectors, and we can basically, technically we can performing the high-dimensional, testing on this vectorized vectors, right? So there's some classic tests such as BS tests, but the issue with those tests is they generally have a very strict assumptions on the covariance, the structure of the covariance matrix, or they have requirements on the sample size. So to tackle those issues, we further, because of the multivariate normality, we're multiplying a Fourier rank matrix onto these high-dimensional vectors. The reason we want to do that is that, first of all, we get this Fourier rank matrix, we utilize principal component analysis. The reason we can do that is that the additive manufacturing generally have a very strong representative deviation at locally for certain process settings. So which meaning this point cloud, even though it's high-dimensional space, located in the high-dimensional space, should have a representation in the lower dimensional space. Right? So therefore, we have an equivalent form, so we project the high-dimensional vector into the lower dimensional space. Now we can performing the Hotelian's t-test to test whether there's any difference regarding the different process settings. Right? So let's take a look at the power analysis for this hypothesis testing framework. Here is our testing procedure, which is more powerful when compared to other popular tests, such as the Goodall's F-test, which is very popular in statistical shape analysis. Goodall's F-test is around here. And also permutation test is also another one that without any assumptions on the distribution, the performance is around here, but our projection-based test has the most powerful result when it's statistically more powerful when compared to the others. Not mentioning the BS test is around here. It's not that sensitive because of the strict assumptions, right? So let's take a look at the case study under this framework, right? So here we comparing the geometric accuracy of two printed utilizing the fused filament fabrication process, and we want to compare one single process parameter, that is a layer thickness. The reason we choose that is that layer thickness is a very important process parameter for 3D printing. It's an influence of printing speed, influence the printing time, and most importantly, it's influencing the printing accuracy and also the resolution. Right? So here we're testing two settings, 0.18 millimeters and 0.38 millimeters. One is a large value, the other one is relatively small. So for each setting, we printed 20 samples, and the p-value is quite significant, meaning there's a significant difference between these two settings. But here's a counterintuitive results. Generally speaking, if we have a smaller printing, layer thickness, meaning we expect we have more details, more resolution in terms of printing. But the bad thing is that according to real result, it's taking much more printing time because there's more layers, and also the deviation is much larger when compared to the larger layer thickness, right? So if you're outside additive manufacturing, you maybe find this result is counterintuitive because according to our idea, the smaller layer thickness should give us a better result, right? So the reason is actually behind this. So additive manufacturing, again, is slicing the design layer by layer. So we have In ideal case, we have ideal layer thickness, right? But in reality, there are some deviations and some random errors. So in other words, if we have smaller layer thickness, then we generally have more layers. More layers meaning these deviation and random error will stack up, so which may provide a more deviation or more variance into this design. Right? So the key points or key takeaway here is that the smaller layer thickness is generally give a good resolution, very high resolution, but this does not necessarily give you a better printing results. Right? So this one raises some very interesting questions, like what would be the best option for printing? Considering with higher layer thickness, we have less printing time and better accuracy. Right? And also, what would be the best option if we consider additive manufacturing as in the hybrid manufacturing setting, meaning the additive manufacturing with a smaller printing time, we have a rough objects, and let the machining do the details, the finer details, right? How to do that? Sorry. The other one comes from our framework is this data visualization tool. It's more like a byproduct of this hypothesis testing. So here, if you take a serious look at here, you can see there's a patterns around this region. It's not quite obvious, but it's much more obvious around this region. The idea is that this printing is, we have some lattice structure inside this printing. Because here we have a 45 degree, meaning passing this degree, then because of gravity, the material tend to be dropping down. The manufacturers have some algorithms to solve that issue, but around this area, they did a very bad job. So therefore, we can actually extracting the manufacturer's signatures from this point cloud so that we can identify the issues and also find a way to improve the manufacturing processes. All right? Some of the, due to time limitation, there's some other works, of mine that's focusing on GD&T, the geometric dimension and tolerancing. Basically, for prismatic features, we developed a set of algorithms to do to extract the tolerance from the physical parts so that we can have a better estimation for remanufacturing. And also we identified there's a gap regarding the freeform tolerance specification for freeform objects. So we utilize parametric bootstrapping for uncertainty quantification and also develop a whole framework how to specify tolerance for freeforms or for freeform surfaces or for intricate features. Okay, as a summary, we have proposed this volumetric data analysis to provide full access to point clouds. We also propose a very accurate reverse engineering model to estimate the original design. We even have an optimization model for to answer the critical process planning problems in reverse engineering. Also, we utilize local geometric descriptors as a feature to predict the variance of the point clouds to representing the manufacturing signatures or scanning signatures, right? And finally, we propose a more powerful projection-based statistic can be utilized for comparison study in high-dimensional size and shape space. Okay, now let's shift our focus a little bit again to talk about some of our current work extended for artificial intelligence. Of course, it's reverse engineering. There's still a lot of opportunities here, such as repair, such as remanufacturing, such as security by design. But also, we are doing some other works funded by other federal agencies. The first one would be this knowledge engineering for rapid qualification of metal additive manufacturing processes. The reason we have this one is that additive manufacturing has a lot of parameters, a lot of models to help us for qualification or certification purposes. But still, how to merge this different knowledge together, we need some extra process on that. Our solution is funded by NIST, National Institute of Standards and Technology, is to build a knowledge engineering framework, which meaning because there's constantly updating of the knowledge regarding additive manufacturing, so we utilize natural language processing to directly parse the knowledge from the papers, which is we consider as distilled expert knowledge. We parse those to construct a knowledge graph, and this knowledge graph is represented by probabilistic knowledge model. And then we utilize the ontology provided by NIST to merge this different knowledge graph to have a complete knowledge graph for the whole metal additive manufacturing community so that we can utilize for inference or decision-making purposes. Some of our prior study, some preliminary results. So here we have one paper to graph. So we have this graph representing the knowledge from one paper, and also we are inputting, 3-4 papers into this automated processing module so that we can have a more dynamic structure with constantly updating knowledge. The other one we're also working on is a human autonomy teaming. This one we're still focusing on vision tasks. So what we want to do is that we identify some issues with the current progress in terms of machine learning and deep learning. So we want to incorporate some flexibility and some human knowledge into the framework to improve the performance of the machine learning model, right? So we are considering two, biological or human knowledge into this framework. The first one is called human in the loop, that we directly incorporate the eye tracking data into the image segmentation tasks. The other one would be the visual question answering, that we do this, for example, the image captioning. We want to incorporate some questions into the consideration so that it can tune the machine learning model to the correct direction. One of the small projects funded by the Greater Brownsville Incentive Program is to develop this human-in-the-loop AI for the decaking process. So what we do is that we want, in powder bed additive manufacturing, we need to clean the powders from the build bed, right? So, but the issue is that the powders, if you take a look at this image, the powder and the part, it looks very similar. The texture is very similar. The color is very similar. So it's really hard to do image segmentation. So here, with the conventional image segmentation, this is the best what we can do, right? So the way we tackle this issue is incorporating the eye tracking data by letting the operator looking at this image for a few minutes to identify what is the patterns. According to the operator, what would be the patterns we want to observe. So here we incorporating some of the eye tracking data so we can treat this data as a prior information for segmentation purposes, right? Lastly, we have this the collaborative robotics and swarm manufacturing that we're setting up right now. We are focusing on wear arc additive manufacturing. So the problem we want to tackle is regarding the residual stress caused by, the geometric distortion caused by the residual stress. What we do is to have three printer heads printing together with asynchronized fashion so that the heat could compensate each other to lower down the cooling rate for each track, and also providing the force to stabilize the process. At the same time, we were talking about introducing the ultrasonic vibration to reduce the residual stress in these cooling tracks. And also further step, we have this more manufacturing idea that we kind of inspired by the Oak Ridge National Lab. We talk about collaboration with them. That is rather than have the robot mounted on the ground, we have the robot is moving and also compensate each other so that we have much more flexibility and a degree of freedoms for the robotic printing process. Finally, I want to give us some appreciation of our funding agencies. First of all, I want to thank the Department of Defense and Department of Energy help us, funded us through the iDream 40 and Careers Consortium. And also we'd like to thank NIST to help us, to funded us regarding the rapid qualification task for additive manufacturing. And finally, the Greater Brownsville Incentive Corporation help us to do research in, in human autonomy teaming. Okay, so that's all I have. Thank you all for listening to my seminar. Thank you.
For this very informative talk. Any questions?
Yeah, thank you. You talked about a lot of things. So I'm intrigued by this landmarks, the landmarks concept, and then you sort of say, okay, and you use it in many places that they, under some conditions anyway, because it seems like a very strong statement to say that, once you do this, they have this sort of coordinate-wise independent after you do the landmarks. So I guess this is you need some conditions for this to be true. Can you just maybe give us some intuition about why this works?
Okay, so the whole idea is that actually there's two assumptions in this theorem. First of all is that the density of the landmarks need to be high. It need to be located in the high-dimensional space. The other one is that for each landmarks, the variation should be smaller when compared to the global geometric variation. So which is reasonable for manufacturing. It may not be reasonable for biological applications, but it's definitely useful for for additive manufacturing purposes because variation is generally small. That is two. So width that's high dimensional. So it's if you take a look at sizes and shape space, it's generally a high dimensional sphere in the high dimensional space. So with that small variation, with those two assumptions in the high dimensional space, it's looking like a sphere located in there. So that's why we can have an approximate normality for that. And also in the high dimensional space, if you take a look at this, because of small variations, in the high dimensional space, all the coordinates is actually independent with each other.
So actually, I have a question more related to the problem formulation regarding why do you need to first predetermine the number of like m and n. In my understanding, it should be more like a sequential step. Based on, for example, if you give an example for like making a teeth implant, right? You make a mold, and based on the mold scan, you can try to see the variation. If any place is unreasonable, then you can redo the mold. So in your cases, because you do multiple scan, like multiple M, right? And based on the scan, you can actually analyze the variation, try to see if the scan is sufficient. Oh, you need a multiple scan. That data should be available. So why do you still need to predetermine the number of M and N before, instead of just looking at the scan data and then sequentially decide if any additional M are needed?
Yeah, actually, that problem is actually a sequential problem. I think I didn't mention about this, but it's generally a sequential problem. That's why in the in the constraints, we have extrapolation of the covariance matrix. So it's, we are tuning, we're tuning the M and N so that it can be extrapolated. But I think I understand your question regarding why this one is to be determined in advance, is that we need to have, for example, in dental applications, right, we scan multiple times. For example, if you stop at 9 times, and I'll stop at 9 scans, but your accuracy requirement is actually 10 to make sure that this one is, with high precision, right? So, but you do not have that knowledge. So this process planning gave you the some help for the practitioner. Say, with that, you need this number of scans, because every, for the scanning task, for the scanners, not scanners, the operators who is performing scanning may not have this experience, like when to stop, and also they do not know like what is the accuracy of this, current model looks like. So that, and also the other one is that we kind of also identify the issue regarding like whether they can do it sequentially rather than have this process planning. So that's why we have this automated variance modeling for the scanning model, so that no matter when the scanner is stopped, then we can have a uncertainty quantification for that model to assist the practitioner whether you need to extra scans or you can stop right now.
Yeah, I have a quick question. Can you give us some example of the application of reverse engineering?
Okay.
I understand in biomedical area we have a lot of application,
yep.
But in biomedical area, the parts is unique, right? We don't have two duplicated parts. Each person is unique. But beyond the biomedical area, so what are the main application areas of reverse engineering? Why people need to care about this area?
Yeah, so actually this one is reverse engineering is very popular for, defense-related applications. For defense manufacturers, generally they have some very old technology, like dated several decades ago, but they do not have access to the original design. Now they were talking about, if we have this part is broken, how can you remanufacture this part without this design? Or whether they want to do a part consolidation. For example, we have 2 sub-assemblies, and then right now, because of additive manufacturing, rather than doing sub-assemblies, we can directly consolidate them together so that we can fabricate a single part. I think GE is doing that right now. So that's reverse engineering, tells that how to find out the original design, and then how can we, based on the design intention, can we consolidate those. That is one application.
But this area will eventually die, right? Eventually, the legacy system will just phase it out, have a new system.
Yeah, of course.
Yeah, this is not a application area for the future.
Yeah. The other application, actually the other major application called by the Department of Defense is regarding repair, especially for Navy applications. They have a lot of degradation of their marine structures. So they want to, rather than fabricating the whole boat, they want to do repair. So the reverse engineering help them to identify where is the challenges, or where are the defects, so that start from the reverse engineering, we can reconstruct the design, so that we can utilize machining to clean the surface first, and then to deposit the material, utilize additive manufacturing. But everything is start from the reverse engineering, from the scanning process, to know where the defects, and also do some classification, like what's the type of defects and how to do the process planning for them.
Any more questions? Okay, so let's thanks for our speaker again. Thank you very much.